Okay, so if you're watching this video, you're stuck on how we deal with sine of an angle plus itself. Okay, if you don't like deltas, you can just think of this as sine of a plus a. And if you've been doing anything with the previous summation identities, which you should have, this problem comes towards the end of the homework. If you've been doing all this stuff with summation identities of sine a plus b, sine a minus b, what you're stuck on now is actually easier. This is a simpler version of that, where all I'm doing is I'm saying instead of a plus b, it's just a plus a. So the angles are actually the same, they're not different, which makes this easier to keep track of, not harder. So remember here, you know what, I'm going to grab this guy. We're going to use this. Okay, you come over here. Okay, paste, there we go. Sines can't change sines. Okay, so we're going to take that idea of sines can't change sines and use equal angles. So everywhere you see a b, I'm going to put a. Sine of a plus a equals sine a cos a plus cos a sine a. Sines can't change sines, which simplifies because sine a times cosine a is the same as cosine a times the sine of a. Just like 2 times 3 equals 3 times 2, right? It doesn't matter what order you multiply things in, which means I can rearrange the order of the multiplication into sine a cos a plus sine a cos a, which is even simpler. That's 2 times sine a cos a. That is what the sine of 2a equals, okay? This turns out to be a very important identity. It's called the double angle identity. And I would like you to go ahead and invent, or no, I want you to discover, we're not inventing math, I want you to discover the identities for cosine and tangent, the double angle identities for those also, by just going through this technique and plugging in the same angle for a and b for those summation identities.